Yeah, so then what the author does is that it equates the equation, I don't know what is the number, let's say equation 1 and equation 2, and then he gets an expression which relates the energy density in terms of specific intensity. And if we want to calculate the space, space or specific energy density across all solid angles, then we have to integrate. And so he has done the same here, and then afterwards he has replaced this u in terms of omega with the expression that is here in 1.6. And then he defines a new term which is a mean intensity j nu. So j nu is basically equal to 1 by 4 pi into integration of I nu d omega. So this is a mean intensity across all solid angles, uh, as it is mentioned. So after defining this new term, this expression changes into 1 point, similar to 1.9. And since this is a specific energy density, so the total energy density is calculated when we integrate in a certain bandwidth, and then we get a relation as shown in equation 1.9. So, and this J nu is equal to I nu when we consider an isotropic case, because then I nu will not be a function of a solid angle, or it doesn't depend any direction. So it will be not be a function of solid angle. So this J nu will become I nu as I nu will come out, and this d omega will be integrated across all solid angles. So this 4 pi and 4 pi will get cancelled, and J nu will equal to I nu. Why I'm saying this? Because the author will talk about this in the subsequent section.
Yes. So,
So
just let me highlight a little bit here. This very important relationship. If you could scroll up a little bit. So this argument about the energy density as a function of direction, which was strange, is only meant to write equation 1.7. So equation 1.7 is very important. It relates the mean specific intensity, which is a very important quantity, with the energy density. So basically the mean intensity is just the same as the energy density, right? It's a very similar quantity. They're just differed by constants, okay? So that's a very important fact to bear in mind. Now we could go on. Pratyush, you're doing this very well, so thanks very much. But I would like to see the others participate also. So if they want to, nobody's forced to participate. But would anyone like to continue to take over from where Pratyush has left at the moment, and talk about the radiation pressure and describe what's in the textbook?
Yeah. So anybody wants to?
I can do it if no one else wants.
Bueno, gracias, Felipe. So please bear in mind that we all need to participate, and to make this more fun for all. And if you're not participating today, then bear in mind that it's important to do so for next lecture.
Okay, I'm going to delete that. So from here, radiation pressure.
Yes, please. Mm-hmm.
Okay, so the radiation pressure is it comes from it's related to the component of the momentum on the reflection of an enclosure. So in this part, we'll be talking about radiation that it is inside an enclosure, a reflective enclosure. So the radiative energy, the photons, can get out of this enclosure. So every time a photon gets how do you say, the crash, it crashes into the barrier, into the mirror, then it's reflected, and the component of the momentum that is normal to to the enclosure, it gets reflected on the other side. So for every momentum that for every component of the momentum, the difference in momentum is twice that. So actually have a,
So you say
and here's
hit
the
rather than crash. It's better to say hit. On the
hit.
foot.
Okay.
Yeah, it just hit.
Yes. Can you see the other thing I'm sharing?
No, we only have your window on the text only.
Okay.
Mhm.
Sorry. How about now?
Oh yeah, that's clear now. Yes, yes.
Okay.
We,
So here.
yeah.
Now this is the same exercise that is on the textbook, only on my whiteboard. So for every time a photon hits on the enclosure, the difference in momentum is twice the component of the momentum normal to the enclosure. So the component normal to the enclosure is this integral over here with the second momentum of the cosine, and the 2 that is because it hits 2 times, because the difference in momentum is twice that.
Yep.
So in this case, inside the enclosure there is an isotropic radiation. So that means that the radiation goes everywhere, in every direction the same. So the mean across all directions is constant. So this value of I is constant and can get out of it's equal to J, and it's constant all across the enclosure. So it can get out of the integral.
In that case, yes,
We
for
get
isotropic radiation, yes.
for isotropic radiation. So then we get the integral here, that is the solid angle. I separated into the second angles with the sine of theta and the other angle, which I forgot this name.
Phi.
Phi. And then we can do the phi integration leads to pi, so we get 4 pi j outside. And for the other integral, we use a change of variables, cosine of theta. And these are the change of variables, the change of limits, and the integration. And this change of variables leads a -1, which I use to interchange the limits of the integration. And this is the integral that we have to use. There's the result. And now that the integral is ready, I can identify this. As the energy density, and this here is 1/3, which leads to a third of the energy density is the difference in momentum here.
Bacán. Muchas gracias, Felipe, por aclarar esto. Thanks very much.
Welcome. So that's why the angular integration leads to this.
Okay, so we have a relationship between the radiation pressure. Can you scroll down? I mean, back up a little bit. Let's see. Okay. So previously we had written the transport of momentum. Okay, so that was the flux of momentum in the direction of of the surface area. How do we relate this to the pressure? Why is this equal to the pressure? Because here we are converting flux of momentum projected on the surface element. So okay, so we already knew that we had the same expression, but without the factor of 2, because now this factor of 2 comes from the bouncing, as you well explained it, Felipe. Now that gives us the transport and the reflection of momentum. Why would that be equal to, how is that related to the pressure?
Okay, so the answer is, where is it? Okay, so here, the flux of momentum normal to an element of area is the pressure here is the momentum per unit of time per unit of area. So the change in momentum is what we call the force. So the force per unit of area is the pressure. So the change in momentum per unit of time, let's say the flux momentum because the flux momentum in an aerial element is how much momentum it gets through. And in this case, it doesn't get through, it gets reflected. So that is the change in momentum per unit of time and per unit of area, which we call pressure.
Is that clear to everyone? I think it would be. So thanks very much, Felipe, for clarifying this. Do you mind to continue a little bit, or?
Yes, sure. Where were we here? So these results, it's going to be important. It says it's going to be important because the radiation pressure of an isotropic radiation field, that's this result, that is the radiation pressure is a third of the energy density, is going to be useful when we discuss thermodynamics of the black body radiation. But I think that's further along the way. So it's important to keep in mind, but not still much. Now the next important to calculate thing is the constancy of the specific intensity along rays in the free space. So here in the title, we can see that everything of that is important to highlight, which is there is a constancy. So the derivative along the ray. So along the direction of that the photons are traveling is constant, is 0. The other thing that needs to be highlighted is that this is free space, so there's nothing, so it's vacuum, there's no particles, there's nothing along where the ray is traveling. So with this in mind, we can consider one ray of light along any 2 points. And we're going to show the other image because I also did this.
Buena, excelente.
So here, and we're going to consider a light source that's somewhere in the space, but we're outside. So between these 2 points, here in X and X prime, we call this. So along these 2 points, there is a light source. There is light radiation that is going from here to the other. Now, this area element is constructed with this solid angle, and R is the distance between these 2 points in the direction K. And the second area element, which doesn't have to be the same area element, is on this other position, X prime, and is used on this other area solid angle element. Now the relation between these 2 area elements is right here. So the second area element is made from the first area solid angle element.
Yes.
As you can see here. So this solid angle, we can move this, distance, and we get the other area element. Is that clear? I think, okay, this is important then, afterwards. So this is the doodle of the diagram of the exercise. And in between these 2 points, there is nothing, there's free space. So there's nothing more to be considered here. Now, the energy, so as there's no more energy getting transferred, other than the photons going from here to here, then the energy that goes through the first area elements is the same as the energy that goes through the second. So here in equation A, I wrote down the energy that goes through the first area element, and equation B, the second, the energy that goes through the second area element. Now, if these two are the same because we are in free space, then some parts of then this gets these are equal, and this is the equation that we get. Now, the important step here is that I multiply by the distance squared here. I didn't. And let's think that there is a 2 here and here. I didn't write it down.
Okay.
Now this element, a solid angle with the distance squared, is equal to the second area element here. So this gets canceled with this, and the same goes from here to here.
So Felipe, thank you very much for going again through this demonstration. I think you did it very well. But I have a question for you, or maybe for someone else. I mean, let's try and answer this question. Why are the two energy elements equal? Why is it that the first dE is the same as the second dE? Because the first dE is the flux of energy evaluated at point X, whereas the second dE is that evaluated at point X prime. Why are they equal?
I think they're equal because this is the energy that crosses along this direction. So it's along the same ray, and this area, and so the energy goes through here first, and the photons that gets from here, that travel from this distance, are the same photons that go through the second area element. So it's the same photons, and the energy of the photon is a constant. So if there are the same photons that goes from the one area element to the other, then the energies that are the same.
Yes. Yes. So I mean, it's what you say, Felipe. But somehow I find it rather confusing because in the first position we are or defining the solid angle towards the right as we look at your blackboard, whereas in the second solid angle, we are defining it towards the left, which might seem a little bit confusing. So the way I understand this is that it's exactly as you say, Felipe, it's important to bear in mind that we are talking about an array and that photons travel in the same direction here, okay? And so when we write down the first expression for the energy, that's A, the expression A, this is the standard definition of the specific intensity. Here we have no issue. This is clear, okay? For expression B then, but no, then here it's a little bit different. Once again, it's the same expression, except that the solid angle is reversed. It's pointing in the direction where the photons are coming from, okay? that might seem a little bit puzzling, okay? But what equation B is trying to convey is that all of the energy that's crossing dA prime must come from dA. So if you're standing on X prime and you're saying, you know, this is the only source of radiation all that's crossing dA prime has gone through dA. Okay, so then you can calculate. Okay, so how much specific intensity will be crossing dA prime by writing expression B. You know, you say you're standing on dA prime at X prime. You know. And you say, well, you know, all the energy that's going to cross dA prime, is that coming from dA? You know, and that is why we will write down this expression B, which is the same as A, but with the solid angle reversed in the direction of propagation. Because you're saying that what's crossing dA prime must have come through dA, okay? And conversely, when you write equation A, you write down, you don't choose any solid angle. You choose that part of that solid angle which subtends dA prime, right? So d omega here subtends dA prime. So this is a rather subtle argument. I think everyone needs to sit down and convince themselves of this proof. It's not so easy to explain, really. But I think, Felipe, you've done a great job, much better than I did last week. So thanks very much for that. I think we can go back to the textbook now.
Professor, could you repeat again? So the internet was not stable here, so I missed some of the questions, so I didn't understand fully.
Okay, so I'll explain again. So this is what Felipe has shown us here is the standard proof for the constancy of specific intensity along a given ray in the absence of interaction with matter. Okay, and the proof it's almost how do you call this? It's almost like a tautology. I mean, it's based on this. We write down this definition of specific intensity twice. We write it down at X and we write it down at X prime. Now, the trick here is to choose the solid angles d omega and d omega prime carefully. As Felipe said, area element dA and dA prime can be random. Then do not need to be orthogonal. In the proof I gave last week, I chose them orthogonal for simplicity, okay? But this is it can be general, okay? So the idea is that first for equation A, we write down the expression for the energy that's crossing dA and that's traveling towards dA prime. So expression A is the energy that crosses dA and that will eventually cross A prime. Is that clear? Yep. Okay.
Yes.
Okay. Now then again, knowing this, we write down the expression for the energy that crosses dA prime. Okay, and it's the same as the definition, but this time we know that normally, Felipe, I don't know if you can you edit, or can you write on your like make an annotation here?
I can't.
You cannot. Okay, well,
I don't know how. Sorry.
Normally with
That's why I did it on a whiteboard.
With Zoom, you can click. It should be somewhere on top of your window, and there's an option to say annotations. Yeah, that's right. That's right. Exactly. Can you place a prime? Write DE prime, and in second expression for DE, add a prime there. Yes, that's what I meant. Well, okay. It's interesting. We do the primes in the other direction. I do. Okay.
You do it like here.
Yeah, no, that's okay. That's okay. You're consistent. The other primes are also in the same direction. This is the when you write down the definition, if you place primes everywhere, then that would be DE prime and evaluated at X prime, right? Now we are going to choose d omega prime, so that d omega prime is as drawn here in Felipe's drawing here. D omega prime is circled in red, and it is the solid angle that's subtended by dA when you look at it from dA prime. Can you all see that? You know, on X prime, you know, and yes. So okay. So that would be the amount of energy that crosses dA prime, and that's coming from dA. Okay. Why do I say coming from instead of going towards? I say coming from because if you pay attention, like Felipe, can you draw a vector representing k, the vector k?
It's
I know
there
it's
in
already
blue.
there. It's there. It's there. Yeah,
It's
we can
already
see
there.
it. Yeah, it's
It's
already there. Okay.
My,
So can you see
my
it?
blue
So
one was dying.
yes, exactly. Okay. So what I say coming from, because in this case, the solid angle d omega prime is pointing in the other direction than k. Okay. So really, to be specific, this when we write equation dE prime, we should have placed here in the argument of I nu of k x prime, we should have written here I nu of minus k. Okay, because it's pointing in the other direction. That's why I say, since the dot product between minus k and dA prime would be negative, and that's why I'm changing the expression. I'm saying it's coming from instead of going towards. Okay, but what is important to understand here is that dE prime, written like as it is at the moment, you know, represents the energy that's crossing dA prime, and that's coming from dA, because we are using the solid angle that subtends dA, okay? And now we use the idea that nothing happens in between, that the other photons that cross dA in the direction of dA prime must be the same as those that are crossing dA prime from the direction of dA. And then we replace dE equals dE prime. And this is how we write finally the equations that Felipe wrote as A equals V.
Okay, Professor, then second question, suppose on the left side of this column or the left disk, you can say the left disk, suppose we have a source, let's say a sun is there. So if sun is pointing towards the left disk, so then what solid angle that then we will form, because now the rays will be coming from the source, so the solid angle will be like taking the area of sun and then it's coming to the disk, because
Pratyush, I think this expression here is general for any specific intensity
Yes,
field. I think, is this what you mean, Pratyush?
do you mean this? Because this is the sun in the, or the light
yes.
source.
Oh, right, that's right. You have the sun already there. Yeah.
Yeah, okay. So suppose yeah, so now the solid angle that will be subtended on the left disk, because now the rays will be coming towards the left disk, very similar to the argument that we proposed for the right disk. So now the rays will be coming in the left disk, so the solid angle that we will take would be uh, like this. How do
Yes. Yes. Okay. I
So
think.
so I think you're saying that this solid angle that comes from the light source from the sun is different than the solid angle in the between these two.
Yes, yes, yes. Is it?
Okay.
Is it? If I'm wrong, please correct me.
I think not.
So
Because the similar argument will be now, it will be a similar argument that we are giving for the right disk when it's inside a certain column or whatever you can say, because now the same argument will follow for the left disk as well, because now we have put another source leftward of disk one. Don't you think?
So you're saying that if this angle is different than this one, then we can say there's a third solid angle that comes from the light source towards to make the second here. So there's
no, only the left,
no.
only the left, only the left disk. I don't know how to draw.
Pratyush, I think that are you proposing an alternative way to make this proof, or is it a question about what happens in this case?
It is a question. I'm not proposing another proof or.
Okay. So like this is a specific example that you're proposing to us at the moment. Can you see that? You're saying, suppose that you have a sun to the left that's shining on the dA surface element, okay?
Yes, yes.
So that is a specific case. It's an example of specific intensity field. The way we've written it, I nu of K at the position X is a general expression. It is valid for any radiation field. Wherever you place the sources, could be one sun, could be 1,000 suns, could be a nebula. We could be inside the sun. It's just a general expression for I nu. Okay? So when you, for instance, when you say, well, okay, but if I place the sun to the left and imagine that it's shining on dA, all right, so we can imagine the sun is a point source at the vertex of the cone that Philippe has written for us. Okay, yes, that's a point source there, and it's shining on dA, and so we can imagine rays crossing dA, all with different orientations. Yes, okay.
Yes.
Some of these rays are the ones that are going to cross dA prime.
Yeah. Yes.
Okay. And so the solid angle d omega, the original solid angle d omega, that one, Felipe, thank you, okay, is defined with an origin on dA, okay? So that's important to understand. Now, if the sun is infinitely far away, then I nu is almost like a delta function going straight ahead, and it's there's no radiation field in the neighboring direction. But that's an extreme case when it's infinitely far away. Okay.
Mm-hmm.
Yes.
But for example, if the light source is not infinitely far away, then this solid angle here then there's a solid angle that's going to create this area, the first area element, and then the second area element, which is going to be a continuation of this angle, of the first solid angle that made the first. So
Felipe, what I meant to say.
Yes.
So Felipe, what I meant to say is that suppose for the element dA, if the rays are coming on from the left side, then we will use the solid angle that you have mentioned in the light blue color. And if we assume that the rays are going towards dA element, then we take the solid angle as d omega. Is it?
I think yes, because I think that in that case this angle is the same as this one, because they are the solid angle element is it means the direction. It means the direction of K. So
yes,
there are rays that are going in K direction within this solid angle.
So be careful there. I mean,
they're going in the same direction. We can say, because the rays are inside this solid angle, we can say that those rays are going in K direction.
That's correct. But bear in mind that the size of the solid angle that's around that direction could change. I mean, d omega is not equals to d omega prime, because the dA is not necessarily equal to the dA prime. Okay. So when we say we write down a solid angle, we also mean it's centered on a direction. It's not any solid angle. I mean, solid angle can have any shape, right? You can draw a surface on the sphere with a complex surface. In general, solid angle can have any shape, but here we mean a solid angle centered on a direction. Okay. So I think to summarize, these are tricky concepts. Most of you have already seen the idea of specific intensity and mean intensity and flux and all that. But these are really tricky concepts. You have to be very careful what you mean when you do astrophysics with them eventually, you know, and you have to calculate a flux. Then you wonder, should I use the cos theta or not? At the end of the last lecture, I expanded on those subtleties. Depends on what you mean exactly. Okay, have to be careful. We'll start doing radiative transfer, and you'll get a feeling of how subtle it can get. But for now, we simply have to remember that the way we write the specific intensity field encapsulates all those issues about where is the radiation field and how exactly is the shape of the radiation pattern. Okay, it can be any radiation pattern, because we are writing down the specific intensity field as a function of direction and position. So if we are standing on dA, you know, then okay, some rays will be going into direction I mean, towards, well, whatever direction, you know, I mean, it's a range of directions going through dA, okay? So, I don't know if this is, if this explains things a little bit better. Maybe Felipe, if you could draw the following. Can you clear your drawings? You still online?
Yes. Clear all drawings. Okay. Good.
Okay. Let's take Patu's example once again. Let's place a sun, but do not put it on the axis. Let's place a sun like a point source. Yes, over there. Exactly. Let's put it there. Okay. Now let it shine on dA. So let's draw an example light ray that crosses dA, but not going through the origin of dA. Let it cross at some other point inside dA. Yes, that one, for instance, exactly. Okay. Okay, so that ray would cross dA. Okay. And when you draw a direction vector corresponding to that ray, it's going to be like a k unit vector. You can write it down, Felipe, please. Yes, k unit vector. Exactly. Okay, and then thank you. And that when you calculate expression dA, sorry, when you calculate expression A for the specific intensity field dE, that is the total energy that's crossing dA, including a range of direction that's dependent in this solid angle d omega. Okay, so if we now draw in the same color, Felipe, draw a new solid angle, a d omega prime segunda, but in the direction d omega, in the direction of k. Yes, that's not what I meant, Felipe. Sorry, centered on dA. Or maybe I should draw it.
dA and dA. Okay. Okay.
If you want, I can draw it.
Can you try it?
Yes, I mean, maybe not on your Blackboard, but I'm just stop sharing and I'll use my tablet.
No, I think that's what you meant.
No, what I'm trying to explain is that
okay, yes,
maybe I
can
should
stop sharing and you can.
Yeah.
But you can also annotate from from your computer, Professor, on the screen of Felipe.
I can try. Okay, let's try. Let's try.
I think just maybe give
Remote.
mouse control to Simon Casas. Yes.
And it's not necessary. It's also there is also an option of annotate in the upper side of the
Yeah, it's true that there is normally, but I can't see it right now. I'm on Linux, and sometimes it's not exactly as.
Oh, okay.
Yeah, I mean, share screen maybe here. Multiple sharing options. No. Yeah, I see what you mean, but I can't see this. I can't see the menu right now. I don't know why.
Yes, Benjamin is annotating now.
Yes,
Uh,
but
Wow, I didn't know that.
view options
Maybe
maybe
from
here.
YouTube.
Annotate. I've got it here. Can you see
yes,
that?
Yes,
Okay,
yes,
wonderful.
great.
Okay.
Well, I'll let you do it then.
Yeah, except I can't undo. Let's see. Let me erase this. What I did. Right.
Great.
So now draw that. Okay. What I meant is that. Okay. So imagine that we have. Well, let's place up. Just not to confuse with the rest of the equations here. That would be dA second, okay? K second. And then I'm gonna draw another solid angle like this. And I'm gonna call this d omega second, like this, okay? Now I'm gonna write dE. It's another expression for the energy density, which is that traveling towards direction k second. So there's going to be I nu of k second in x times d omega second times dA, etc. So what I wanted to explain here is that let's place a sun, like Pratyush suggested, at any location here, for a point source, where we have the red dot, that's shining on dA, okay? So now we have the k second vector here. This vector is crossing dA, okay? Now, the same vector is what I've drawn here, but I've moved it to the center of dA prime, of dA, sorry. This is k second. It's the same vector as this one, but I've moved it to the origin of dA. It's a vector, it's a direction. I can move it around. It does not have to be at the same origin, it's a direction, okay? And so that's why, that's how I meant really, we can construct the specific intensity field for any direction. So even though, right, we have to bear in mind that these are infinitesimal quantities. So we write them as if they were big, you know, because we can draw them, you know. But actually, what I mean to say here is that this ray that's crossing dA does not go through the origin, apparently, but it crosses dA. And so when I write down the energy that's crossing dA, I need to take it into account, okay? In which direction is it traveling to? Well, we know the direction is given by k second, and here is the k second, but it's translated to the origin of dA because this is how we draw it, you know? Is that clearer? Okay, well, again, these are difficult concepts, so maybe it's good if don't feel comfortable with it, think this over and bring up your questions for the next class. I think an hour is already passed, so Felipe, can you return to the textbook?
Return to the textbook. Yes. Oh, the notation is here.
Okay, I have to clear drawings, clear all drawings.
Clear. Okay,
Yeah.
great. Thanks. Constancy, yes. So the rays are constant.
Yes.
But along the ray.
Yes. Okay. So and this is like the starting point for radiative transfer, because then in the next one, I wanted to do this today, but it's important to clarify these things. And we need to start doing radiative transfer and interact with matter. So matter is going to shine into the ray, and matter is going to absorb radiation out of the ray. Okay, and so well, I think that's it for today. The proof of the inverse square law for the uniformly bright sphere is a problem, standard problem. I think please work on this on your own. Maybe Felipe, stop sharing at the moment.
Sure.
Okay. Wait, here we are. Share. Okay, so for next class, I want please everyone to make sure they understand this on themselves. If you have issues working this out, then bring them up for the next lecture, and we'll discuss them. Okay, we'll just start asking whether anyone's got questions about section 1.3. Okay, and then we'll start doing radiative transfer. So I need someone from you to explain, well, you know, absorption, and finally write down the radiative transfer equation. I've also got this in my summary, okay, but I've got them in a slightly different way. So I suggest that we go through how the textbook presents things, and then I'll try to summarize with my lectures, which is a slightly different perspective, okay? But next time, please, if you haven't participated yet, well, bear in mind that the idea is we all participate. I mean, you're not forced to, but it's better for learning, and you know, it's better to be proactive. If you are proactive, then you'll see that it works better. Even if you have not understood, suppose that, you know, like, okay, I've read this 3 times and I still don't understand, then it's still better to participate, because you can say, well, this part is where I'm stuck. This is where I don't understand, okay? And your grade has nothing to do with that. I mean, if you participate by saying that you don't understand, well, that's still participating, you know? So my impression is it's going to be good because you're participating. The worst is just to not say anything, even when you do not understand. That's the worst you can do. Okay. So please bear this in mind, and let's see each other again next Tuesday then. Okay. If it's okay for everyone. Muy bien. Entonces, muchas gracias a todos por participar hoy día de nuevo. Me despido ahora. Goodbye. See you next Tuesday. Ciao. Thanks very much,
Bye.
Felipe. Thanks, Ratush. Ciao.